You see them everywhere, right? On rooftops, in fields. But how do solar panels actually work? Today, we're going to break down the amazing physics that turns pure sunlight directly into electricity. It's called the photovoltaic effect. I mean, seriously, think about it. They're on our homes, powering satellites, even on top of little calculators. But have you ever really stopped to wonder what is happening inside that dark, shiny surface? How does a simple, silent panel just sit there and turn sunlight into usable power? Well, the secret is a beautiful piece of physics known as the photovoltaic effect. Basically, it's the process of converting light directly into electricity, right down at the atomic level. This effect is the engine driving every single solar panel on Earth. So, to really get this, we're going on a journey from the big picture all the way down to the microscopic action. We'll start with sunlight, then dive inside a solar cell, see how a tiny particle of light gets the job done, understand how that creates a current, and finally, we'll zoom back out to see how this idea became a reality. Okay, let's start at the highest level. We've got a solar panel, we've got sunlight. What's the very first thing we need to know about how these two connect? Well, the real magic isn't in the panel as a whole. You see, a solar panel is just a big case holding a bunch of smaller units that are all wired together. These are called solar cells, and that's where all the action really happens. All right, let's zoom in further. Right inside one of these cells, think of it like the engine room of the whole operation. What's it made of, and why does that matter so much? The key ingredient is a semiconductor, usually silicone. But it's not just a simple slice of the stuff. Oh no. This is where engineers get really clever. They modify the silicon to create two very distinct layers that are designed to work together perfectly. On one side, we have what's called N-type silicon. The N is for negative. Easy enough. It's been treated or doped to have a surplus of free-floating electrons. Then, on the other side, we have P-type. And you guessed it, P is for positive. This layer is designed with the exact opposite feature. It has these tiny vacancies or holes where electrons are supposed to be. Now here's where it gets really cool. When you press these two layers together, those extra electrons on the N side immediately see the empty holes on the P side and they jump right over to fill them, but only right there at the boundary. This little shuffle of charge creates a permanent one-way electric field right across that junction, the famous p-n junction. And this is the perfect way to think about it. This field is the secret sauce for the entire operation. It really does act like a slope or a one-way slide. Once an electron gets pushed onto the slide, it can only go in one direction, from the P side to the N side. Remember that slide. It is absolutely crucial. So we've got our cell all set up with its built-in slide. Now it just sits there, waiting for a push. And that push, well, that comes from the sun. You know, sunlight isn't some continuous wave. It's actually made up of countless, tiny, individual packets of energy called photons. You can think of them like microscopic energy bullets just streaming from the sun. So what happens when one of these photon bullets hits our solar cell? First, it zips into the semiconductor material. Then, if it has enough energy, it slams into a silicon atom and bam, it transfers all its energy to one of the atom's electrons. With this sudden jolt of energy, the electron is knocked loose. It breaks free. And when it leaves, it creates a vacancy. And that's the hole we talked about. So the crucial thing here is that every time a photon successfully strikes an atom, it creates two mobile particles, a free negative electron and a free positive hole. This is called an electron-hole pair, and these two are the charge carriers that are going to become our electricity. Okay, so we've got our charged particles, but a bunch of particles just floating around randomly, that isn't electricity. Not yet. We need organized movement. We need a current. So how do we get that? This is where that one-way slide we built comes into play. That electric field at the p-n junction acts like a traffic cop. It immediately grabs our brand new electron-hole pair, it forces the negative electron down the slide toward the N side, and it shoves the positive hole in the opposite direction, toward the P side. This separation is everything, seriously. Without it, the electron would just fall right back into the hole, and all that energy from the photon would just be lost as heat. So by building up all these separated electrons on the N side and all the holes on the P side, we've created an electrical imbalance, a voltage. Now, if we connect these two sides with a wire, the electrons will rush through that wire to get back to the holes on the other side. And that directed, organized flow of electrons through a circuit, well, that is an electric current. We've made electricity. This whole process seems almost magical, but it's actually built on a long, fascinating history of scientific discovery and some seriously clever engineering. The effect was first noticed way back in 1839 by Edmund Becquerel, but it stayed a scientific curiosity for decades. It took almost 50 more years for Charles Fritz to build the very first solid-state solar cell, though it was incredibly inefficient. From there, it's just been a steady march of scientific and engineering progress to get to the powerful silicon cells we use today. So the science is totally sound. But in the real world, things are never quite that simple, are they? Does this elegant process work the same on a cool, sunny day versus a scorching hot one? Now, this is really interesting because it's a little counterintuitive. You'd think more heat, more power, right? Well, not exactly. While the current, that's the flow of electrons, goes up a tiny bit with heat, the voltage, the electrical push, drops off a cliff. The final result? As a solar panel gets hotter, its maximum power output actually decreases. And that's a huge engineering challenge, keeping panels cool so they can operate at their best. So, to wrap it all up, just remember these key things. It starts with a photon from the sun knocking an electron loose. Then our built-in electric field, that one-way slide, is the hero that separates the charges. That separation and directed flow is the electric current. And finally, in the real world, heat is the enemy of efficiency. It's just incredible to think that the key to this modern green technology was discovered nearly 2 centuries ago. It poses a fascinating question, doesn't it? What fundamental discoveries are being made in labs right now that will quietly reshape our worlds 200 years from today?